Okay, so April 16, 3 weeks to go. So we're going to continue our exploration of magnetic fields, how we can determine them from various current distributions. We've already taken the first steps there, which have to do with making use of this expression. I didn't describe it with a name last week, but you'll sometimes see it with a name associated with it, the Biot-Savart law. But this is our basis for determining magnetic fields from current distributions. We started off on Thursday with a couple of instances of determining B fields by integration. You'll remember we did this for a straight wire and then for a circular arc, which might make a complete circle. I'm going to do one more brief extension of that to another integration where we introduce a little bit of complexity by looking at the magnetic field on the axis, not just at the center, but on the axis of a complete current carrying loop. And then we're going to pause and again, I want you to be very much in the mindset of thinking about compare and contrast exercise with what we did with electric fields. You'll remember a month ago roughly, we did electric fields by integration for increasingly complex charge distributions, and then as we were getting to integrals that were getting more and more complex, we introduced a complementary technique that might allow us to find electric fields, in particular in cases that have clear symmetries. So we're going to do the exact same thing now for magnetic fields. We're going to introduce a complementary technique for determining magnetic fields, not really by integration, but by introducing Ampere's law, which will become, in some sense, analogous to Gauss's law. But by what I mean by in some sense is very important that we understand that. So once we've introduced Ampere's law, we're going to play around with it, as we did with Gauss's law. Take some limited number of geometries where the symmetry helps us, and it's even more limited with magnetism than it is with electric fields, largely because of the right-hand rule complexity and the necessity for having motion of charges. So we'll take a look at that. Mostly we'll worry about cases that have cylindrical symmetry. And the reasons for that I hope are becoming obvious, but will become even more so for today. We'll take one brief look at a little bit of a specialized geometry that is of some practical interest, namely a device called a solenoid, basically a helical coil of current carrying wire. A couple of comments only about taking a solenoid and twisting it into another shape, namely a toroid, and then we're done. Okay? So, I don't want you to get too bogged down with the technical details. There are certain special cases that we'll focus on. If you have a good understanding of how to tackle those, more importantly, how to use the results from them, we're in good shape. And then at this point, I think lastly, we'll spend maybe 15, 20 minutes coming back to what we introduced very briefly, namely the idea of an atom, a very simple classical model of an atom as a positively charged stationary nucleus being orbited and classically modeled by electrons going around in circular paths. We'll take a look at that again, see what we can learn about it in terms of the magnetic field associated with such an orbiting electron, and then in a very qualitative way say a little bit more about how this might determine magnetic properties of materials. This last topic is an extremely interesting, rich topic. Sadly, we don't have time to do much of it in this course. For those of you who are going on to do more physics or going on to do anything to do with maybe materials science, you will want to spend some time reading about the interesting phenomena associated with magnetism in materials. There's some sort of rather qualitative text in the textbook. I'm going to add my own quick take on that, and I'm also going to post some notes from another introductory textbook. All of this is going to be FYI, and it's only for those of you who are, again, going on to do more physics or maybe material science in some way or another. Okay, just so you know what those topics might comprise, just to give you a sense of the richness of the phenomena. Ferromagnetism, which we've already briefly talked about, materials that can have some sort of permanent intrinsic magnetism. But then I'll briefly mention, and probably pick up on this at the start of Thursday's class, there are a couple of quick demonstrations I want to show you at that point. Paramagnetism and diamagnetism has to do with when you have multiple molecules in some condensed matter phase, how those magnetic moments associated with the molecules orient with respect to each other, and what effect that has on the materials themselves, but also what happens to them when you put them in external magnetic fields, and lots of cool things. And then lastly, which I have no time to talk about at all, is superconductivity. Sounds like a little bit of a deviation from magnetic phenomena. Just talking about conductivity. Superconductors, as you know, are materials that allow electrical current to flow essentially with zero resistance. Remarkable, possibly remarkably practical, useful devices as well, materials. But it turns out that superconductivity is very much associated with interesting magnetic phenomena as well. Most strikingly, the observation that when materials are superconducting or become superconducting, they do not allow sustained magnetic fields to exist within them at all, at least with one slight exception. So, lots of really interesting materials science related to this, sadly not the topic of this course. So, just wanted to give that plug, advertising for those of you who are doing stuff that may be relevant for. Now's the time to do some background reading, but FYI only for this course. All right, so with that rambling discussion of magnetic phenomena, let's turn our attention back to something very concrete, which is to finish up looking at some magnetic field determinations by direct integration. And again, a reminder that at the end of last Thursday's class, we had taken our the arc length of current carrying wire, maybe it's got current flowing like this. We kind of have to, very often in situations like this, idealize things a little bit. Of course, there's current flowing here, the current has to get in and out of this piece of conductor somehow. And we tend to kind of forget about that sometimes, but we might, for example, have a lead coming in here so that the current connects to this going in, and maybe it comes out in this direction. Try, just be mindful of the fact that somehow there's an idealization here. And maybe that's all we need. So the extension that we did to this, once we found the result for the magnetic field at the center, which is the only place I will ever ask you to try and say something about the magnetic field associated with a current carrying arc, what we've done is do the very straightforward extension of this to a complete current carrying loop. And again, how the current gets there and how it gets out, we didn't spend much time worrying about. But just so you remember, the results that we determined on Thursday, the case of a subtended arc angle phi, the magnetic field at the center is this, and this is in radians. We make use of that arc length, subtended angle, and radius relationship relies on giving the angle phi. And we've extended this to the phi equals a full 2 pi r scenario to get the magnetic field at the center of the current carrying. Okay? So that's where we wrapped up on Thursday last week. I'm rather briefly going to take this now and ask the question, not just what the magnetic field is at the center of this circular loop, but one other place where we can maybe say something without too much difficult calculation is what is the magnetic field anywhere along an axis that is passing through this, this central point. So anywhere along an axis that looks like this. Let's just extend this a little bit. So now we're looking at the B field on the, we call it the perpendicular axis through the center of a current carrying loop. Now, as I'm just writing this up here, what I'm hoping is you're thinking a little bit about the analogous types of calculations we did with electric fields. And in this case, we might have been, let's make this now a full circle and draw it with a different perspective. Let's say we've got it looking something like this. and maybe with some perspective, I'm going to call this maybe the x-axis. This is perpendicular through the center. We're trying to find the magnetic field at this point. Remember, we did something very similar for finding the electric field at a point on the axis, but a certain distance away from a uniformly charged loop of charge. Okay, so exactly the same setup. And of course, what we did was figure out at that point, and again, I'm going back and forth here, the compare and contrast exercise. We've taken a small length element dl, we looked at the amount of charge in there, we figured out what its contribution to the electric field was based on Coulomb's law essentially. We looked at symmetries, and then we've done the integral around the loop. Okay? So we're going to do the exact same thing here, and I'm going to be brief. I'm going to have you guys just read through the page in our textbook rather than do it in class. What's different now? Well, first off, rather than this being an element of static charge, it's now an element of current carrying conductor. Okay? Fine. That's not such an easy, not such a difficult thing to transform into. We've got IDL. We already have this over here, so pretty straightforward. What we're going to have to worry about most trickily is the directionality of the magnetic field here. So it's not easy for me to draw this, so I'm going to try and have you guys imagine it. But let me just take this now and maybe because it's just easiest to visualize, let me turn it to be horizontal. So this is the same current carrying loop. Here now is my axis through the center, and again, we're trying to find the magnetic field at this point. So let me just have you think through the geometry here based on the right-hand rule. Let's say on this side, I've got current flowing into the chalkboard, and on this side, I've got current coming out, and of course it's circulating in this sense. So if I'm looking at this point and this point, what can you tell me about the directions of the magnetic field produced by, let's say, a current carrying length element here, and then we'll look at this and we'll say something about symmetry and adding and canceling components, okay? So take 30 seconds either on your own or preferably talk to your neighbor and see if you can figure out what direction the magnetic field at this point to this small current carrying element is. And then with the exact opposite over here, tell me what the contribution to the magnetic field from this current carrying element is, and then tell me something about your conclusion. Okay, go. Just 30 seconds.
Thumb is the charge.
I think it's because there's two of them. I think you're supposed to do the wrapping one for this.
Thank you.
I mean, I don't know which direction because we're not looking for force. I don't think in this case.
But the field would be in the same direction of force, right? Like
The field is perpendicular. So then if you use this one, it's current, field, source. So like force goes that way, like current goes this way, field goes that way. And the other one is current, and then wrap around is the way of your field. Well, okay, and this side, like if we're doing the one on this side, then it goes in and it goes that way. And then on the other road, it can wrap around this way.
So what's on the direction? So the thumb is what?
The thumb is current.
Okay, 10 seconds left.
And then what's the fingers?
The fingers is the field, like the magnetic field.
Okay, which we're trying to find. And then the palm is...
The palm is nothing in this one. So, I mean, if you hold it flat, I don't think it's this rule. I think the rule you're supposed to use is this one. The magnetic field goes around like...
Okay, let's see what you got.
Yeah.
So,
I think.
let's focus
Unless
on
he
this bit
explains the
first.
opposite.
We've got a small current carrying length element. Current's going into the chalkboard. What direction is the magnetic field that it produces at this point? Directly upwards? Directly upwards. So remember, I only care about the contribution from this little piece of current, not the entire ring. So there's just a little piece of current going into here. What's the direction of the magnetic field that it contributes at this point?
It's going up to the left. Or maybe to the
Up to the left, up to the right. Let's get somebody who's willing to commit. Anyone willing to commit? At the back.
Drama goes down.
We get one more input, but what I want you to be thinking of is this and a concentric circle. that passes through this point. So let me draw this in red, okay. That's a concentric circle. Yes?
Clockwise.
Clockwise. That's clockwise, yes. Okay, so at this point, if that circle has a magnetic field that's circulating clockwise, what direction is the magnetic field at this point? Okay, two people next to each other doing things that are not compatible with each other. Okay, anyone want to commit? Last chance, yes.
Perpendicular to that straight line between
Okay, good, perpendicular to that line, and which direction? All right. So, DB is the L down here, okay? So, a little bit tricky, right? So what I want you to be thinking of is for a small current element here, this is where this type of curled finger right-hand rule works best. This is the direction of your current flow, direction of the thumb. These circulating circles of magnetic field wrap around in the direction of your curled right-hand fingers, okay? So this contributes a small amount of the magnetic field that's in that direction. Okay, let's turn things around. At this point, what does this contribute to the magnetic field? Yes?
Anti-clockwise.
Okay.
About that point.
Okay, good. So again, I'm imagining circles passing through the point of interest. And
Yeah, this
now it's coming this way. So indeed, it's going counterclockwise, so it's contributing
about
to the magnetic field in that direction. Okay?
it's like circular, like
Easy to get
vectors going around.
confused here, but I want you to
Yeah, but
work
the
through this
right-hand road is
exercise.
what
What we
direction
are
it's called.
converging towards is what I think Kate wanted to tell me at the beginning, which is the end result of all of this, which is, of course, we're integrating over the full loop.
Oh, you're
Okay?
and wrapping.
So if we're
Yeah,
integrating over the
you
full
don't know if
loop,
it's clockwise
every
or
point we've got on this loop, there's a point on the other side
I
that
mean, in this case, it
contributes to
doesn't
the
matter.
magnetic field with a
Sometimes you
component in this direction which cancels with its opposite
Figure.
neighbor. So, what's the direction of the resultant magnetic field? Okay, thank you, Mitchell. The resultant magnetic field is in that direction. Okay? Now that's true for anywhere above this disk. If you do this down, again, you're going to have to struggle with the right-hand rule a bit. You're going to find that the magnetic field, again, has components which cancel in the plane of the disk. And they add in the plane that's perpendicular
So then you know
along this axis. Okay?
yeah, well, it's different.
All right, so we know how this goes. We could figure out the strength of this. What do we care about? Well, we've already got the right-hand rule behavior in here. Essentially, we're going to integrate over the full circumference, which is 2 pi r. And we have to put in a 1 over r squared dependence for giving us the magnitude. 1 over little r squared, as in electrostatics, we're going to cast this in terms of big R squared, the radius of this loop, plus x, which is however far away we are from the center of the disk, okay? All of that looks exactly the same as we did with electrostatics. So I'm not going to do it in class, but just tell you what the answer is. And what you're seeing here is that very often we want to decouple probably initial determination of the direction of the magnetic field, taking account of adding and cancelling components. Take care of that up front so you know which direction the magnetic field is pointing, and then simply work with the magnitude. Okay? So you see there's really no explicit directional or vector information in here. We're just working with the magnitude. And if you do this and complete the integral, what you're going to get as a result, and again, I'm not going to do this in class, but it's pretty easy to follow along either in my notes or from the textbook. We get a relationship that looks like this. Okay? So there's the result. The magnetic field, a distance x away from the center, on an axis that passes perpendicularly through the center. It has this 1 over big R squared plus x squared to the 3/2 power. We've seen that before in electrostatics. And then up here depends on the current and depends on the size of the ring. Okay. So no big perhaps surprise. If I take x equals 0, we're going to get back to the same result we had for the field in the center of the loop. So let me just add this as a short caveat. For x equals 0, so this is the center. You remember the result we had from this, the full circular arc, which is that, as expected. Perhaps more interestingly is what happens if we're really far away. And in this case, we find the total magnetic field is mu naught I over 2 r squared over x to the power 3. Okay. So, in this sense, it's already looking quite familiar. It looks somewhat like the electric field we determined for an electric dipole. Okay. So, similar to an electric dipole. All right, so it drops off as 1 over x cubed. So let me just try and draw this qualitatively. This has gotten a little bit messy, so let me try and just redraw it over here. So we have determined at least on axis that the magnetic field is in this direction. Qualitatively, what do you expect the magnetic field to look like, not on axis, but off axis? And tell me just roughly what this picture looks like as a whole. Okay? Magnetic field lines, how do you expect them to look? And you can do a little bit more of this, figure out what the field looks like outside the loop, and then just try and piece this all together and tell me what the overall distribution looks like. Yep. Oh, how do you mean? Let's think about the relative size, however. Let's say I'm off here, for example. So now I'm closer to this current carrying element than I am to this one. Well, perfect cancellation doesn't work anymore. But think about this vector and this vector, or the analogous ones over here. So this is closer, so it's going to have a larger contribution than this one. And so the net is going to be some of these two. Ariel. Say it in slightly different language.
It's going to be like each part of the wire is like an individual straight wire.
Mm-hmm. So in that sense, yes, you expect this to be wrapping around somehow for sure. It has to come back. So the magnetic field has to come back when I'm outside. So that's certainly true. So somehow I expect this to wrap around, and then just with this qualitative argument, what's kind of happening is I'm not in the center, but I'm still inside the loop. What kind of pattern are we constructing here? Or is that just...
Yeah, it's sort of going back, but like back
Okay.
through.
I know this is not easy to say in words, but what you should hopefully be able to see is that it's kind of flaring or spreading out like this, these wrap around, and so we get this sort of pattern. Okay? So in this sense, it's reproducing the pattern of field lines that looks pretty much identical to what we had with a simple bar magnet when we first introduced magnetic field lines. Okay, crappy drawing, but you get the sense of what I'm trying to get across here. Okay, good. All right, so for those of you who are up for a challenge, a little bit masochistic, there's a very interesting example over 3 pages in my notes of a complicated integration of current problem. I will never ask you to do a problem that challenging on a test, but again, for those of you who are up for it, take a look at that. It has to do with a spherical shell, which is carrying current in a kind of lines of latitude pattern, if I've got that the right way, and trying to figure out what the magnetic field associated with that. So it's a complicated integration. Again, for those of you who are up for it, good, but I'm not going to test you on it. All right, let me pause here and just ask for any questions on E fields by direct integration from this expression over on the left side. Yeah.
So can you think of it like normally if you had a wire that was carrying current, like you'd have the B field kind of like going around, like it's like a vector field, and then when you like wrap the wire, it's kind of like you're also bending the.
That's exactly what you're doing, right? So, and you're going to start building up those sorts of pictures a little bit more today when we talk about the magnetic field associated with the solenoid, and then we're going to take solenoid, which in principle is a long cylindrical thing. We're going to take it in exactly the same way, and we're going to wrap it around into a torus. So yes, that's a nice way of thinking about it. Yeah, so that's exactly what the field looks like. Other questions? Okay, so let's turn our attention to Ampere's law, which is this complementary technique for figuring out the B field. Now, let me say a little bit about what Gauss's law did. It's an example of the divergence theorem. It's somehow relating something that's flowing out of a source through a surface to the magnitude of whatever that source is. And then we, of course, apply that to electric field, which originates in electric charge somewhere inside that surface. We'll have a little bit to say about the true Gauss's law for magnetism in a few minutes. For that, now we've got things that are intrinsically at least one-dimensional, namely current flows. Let's take the simplest geometry we can imagine. It's current flowing along a very long straight line. If somehow I wanted to enclose that current, and at least with the same conceptual idea of saying that something that's flowing, that originates with that flowing current, I can somehow quantify by summing it up over some kind of geometry. This is hard for me to say in a way that's not totally obscure. But what might we, instead of a completely closed surface around a static charge distribution, what kind of thing might we be imagining wrapping around our flowing current in a long straight line that in some sense encompasses whatever it is, in this case, a magnetic field that originates from that line of current?
Like the face of a cylinder or something?
Keep thinking about it a little bit. Let's say this is even an infinitely long wire flowing current. So if it was finite, somehow, yes, I might be willing to accept the cylindrical surface, but somehow the current has to get in and out. So don't confine yourself to thinking of just a completely closed surface. Is there some other way that we can somehow enclose just a one-dimensional linear distribution of something?
Like take a slice of it.
A little louder?
Can we take like a slice of the wire, like we did for the electric case, like the current that flows through?
So, I'll try and ask this one last way and then I'll tell you the answer. I just want to somehow completely enclose whatever current flow I have moving along the line. So, does it need to be a closed surface, or can it be another geometry? Okay, that was a disaster. What I care about, it turns out, is all I need is to wrap a loop around it. Okay, so it's not a closed surface, it's just simply a loop through which this current is penetrating.
So like the face of it, like cylinder, like the, or like.
Good try, Noah, good try. In a sense, yes, but I don't even need to make it of finite length. All I need to do is literally make an enclosing ring that doesn't have to have any length in that direction. So if you think about this, now I've gone from something which was static, which of course I can enclose with a closed surface, to something which is an infinitely long line of moving charge, current. So I can't completely enclose that by a surface because it's an infinitely long line. What I can certainly do is wrap a simple ring around it. So this is what Ampere's law does. And so in this sense, it's not Gauss's law. Talk about true Gauss's law for magnetism, but it has the idea of being something that encloses the source of the field, so the current that's produced in the magnetic field. All right, so that rather unsuccessful